continuing on with class number 10, we're going to talk about the modifying factors. These are also often called the Marin factors, M-A-R-I-N, to account for various things that are different between a specimen that's in the laboratory and a endurance situation that we want to calculate. There could be manufacturing differences. There could be different environmental differences, like the temperature. There could be some design differences. It could be for instance, the roughness, the surface condition. That could be also as part of the manufacturing differences you could include. The dimensions can be different. Okay, so we're getting data with a particular size. We'll talk about that some more. I mentioned the surface finish. That's definitely because that's where cracks start. So that's an important thing. So what we have, what follows is a bunch of modifying factors that are in the book. You should check them out yourself and be familiar with them and to navigate them, because they're kind of arranged in a haphazard way. And so if you're using when you go to use them, it might not be 100% as clear as I'm trying to make it, but let's see what happens. All right, so these Marin came up with these factors to adjust the endurance strength. And so this is the main equation right here that converts the SE prime to just SE. So we start out with usually about 0.5, the ultimate strength in the SE prime, and then we adjust with these different factors. The Ka is the surface condition factor. It's equation 619 and in table 6.2. Then KB is a size factor. It also accounts a little bit for the type of loading, and has a little bit of an accounting for whether the thing is rotating or not, because our specimen rotates. So we might not account for that. So we might get an equivalent diameter. Let's say if the thing is rectangular or if it's circular and not rotating too. We also have a load condition. So if it's either in axial or it's in torque, we might put a number on here. If it's in bending, this is equal to 1, because that's what the specimen was doing in the lab. Temperature factor. This actually brings up the idea of creep, which we could bring up in another class at some point. It's a different type of failure mode that requires stress, temperature, and time all together, and it's its own kind of failure. But we have a temperature modification factor. Temperature can actually improve the fatigue up to a certain point, but then it gets worse. Reliability factor. And we'll talk about this some more. This factor doesn't really increase the reliability necessarily. That if you want to predict when something's going to fail, you can't increase the reliability more. You could just increase the reliability that it won't fail. And then in the 10th and 9th editions, and before that, there was a KF here that was very confusing. They took it out, so it's not in the 11th and later editions. But it was there as a placeholder. So here you go. Here's another page doing the same things, but here's just a summary of the equations so we can have them in one place and look back at them. Here's Ka. Note that it uses a lowercase a and a lowercase b. These are not the same as on the previous page. I should get rid of the page number there because we have different editions. These are not the same. You get them from a table. We also have the size factor. Here's just the English version of those. There's a metric version as well. And you can see between size of 0.11 and 2 inches, we have this factor to account for it. And then between 2 inches and 10 inches, which is a large diameter. We can also put an equivalent diameter into that spot, into these Ds that we'll look at. The loading factor is 1 for bending, 0.85 for axial, and 0.59 for torsion. And that's only if there's a single loading condition, we should note. A temperature factor. This is not the same in each of the books, I think. I think there's a little bit of different. This one's to the fourth, has a curve fit to the fourth. In the 11th edition, I think it just has a quadratic. We'll look at those in a minute. We'll look at all of these in a minute. Reliability factor, although there is a Z right here, we can also just look this up in a table. And the miscellaneous factor, use 1 no matter what. Don't get it confused with stress concentration factor, because that's capital K, lowercase f. It's not this thing. Right, so that I'm putting that little warning sign right in there. Boop, boop, boop. Okay. So these slides, I put these together a long time ago. I think I was trying to be funny. So let's just grin and bear it as we go through it. All right, so surface factor, stresses tend to be high at the surface. Surface finish has an impact on the initiation of cracks. For this localized stress concentration, surface factor is a function of ultimate strength, 2, so higher strengths that are more sensitive to rough surfaces. So here it is in the 10th edition. Here are those factors A and B, so the coefficient and the exponent. Once again, not the same thing as that we previously used for the curve fit of the SN diagram, a totally different thing. Here's from the 11th edition and older. You see that there's differences in many of the different values right here. I decided to investigate this just a little bit to see how much of a difference. First, here is from another book that Shigley written, his handbook. So they've show you the curve fit and the amount of scatter that was from the original things that they were grabbed for, right? So here's my graphing of those for the 10th and 11th of equations, right? So you can see, yeah, there is some amount of difference between these. And then this is me superimposing it over that graph right over there. I think I did okay from that. I think maybe it's a little off in the X direction. It needs to be shifted over just a little bit. But hopefully that gives you a little bit better of an insight and idea as to what these things are and how much and how they're related to each other. You also might want to take a moment and look at what the ground versus machine versus hot rolled versus as forged. Interesting. What the ground is so much better because 1 is the better number than the others, right? Because we're reducing these values right here tend to produce a Ka that is less than 1, right? So 1 being the laboratory conditions, something less than 1 reduces the endurance strength. All right, so the size factor, larger parts have a greater surface area at high stress levels, and the likelihood of crack initiation is higher. So that's why we have a size factor. It's obtained from experimental data with a wide scatter. Once again, right? We're worried about the wide scatter. For bending and torsion loads, the trend of the size factor is given by these right here, right? For axial, though, it is equal to 1, right? So it only applies to round rotating diameter. So if you are not rotating or not round, in order to use this size factor, you have to adjust. And you can do that by these right here. These factors out of this table, you find these diameters right in here. And look up into the written part above to be able to see how they're used. And so there's this movie called Raising Arizona, and this guy goes in, one of the criminals goes into this backwoods or off the beaten trail store, and he looks at some balloons and he asks, do these blow up in funny shapes? And so the guy says, do these blow up in funny shapes? And the guy says, well, no, not unless round is funny. See, and that makes me laugh every time. So there you go. You needed to see that. We have the loading factor. So it accounts for the changes in endurance limit for different types of fatigue loading. So we're only doing a bending test in the laboratory. So we might need to account for some these other things, right? So, and also when we're using combination loading. So here are the factors to use. Now, a really interesting one is to take a look at the torsion one and to compare it to something we already know from the distortion energy theory when looking at shear stresses versus normal stresses. And we know that we used a 0.577. And that's not a coincidence that they're near each other. That what is actually when discussing this, that it is a physical connection. That shear strength is tied to normal strength in this area of things, right? So that's if it's not bending, we use an axial of 0.85 and a torsion of 0.59. Temperature factors. Endurance limit appears to maintain the same relation to ultimate strength for elevated temperatures as for room temperatures. Here is that's a weird sentence what they just said right there, because it kind of sounds like the opposite of what we just meant to say. Endurance limit appears to maintain same relation to ultimate strength. Okay, for elevated temperatures as at room temperatures. So there's the 10th edition, which had a table, and you can get this table in here for this KD instead of using this stupid equation. So just use the table. Don't use the equation. And there is a figure that shows you, and you use the ultimate one here, not the yield one. But in the 11th edition, it's a much simpler equation because it's just to the square. So that might not be too bad to do during an exam. But I think it's silly to use this 1 to the 4th. There's a whole lot of chance of getting it wrong or entering it in wrong. And I would definitely use one of the temperatures that's out of the table. And so you didn't have to do that. And also I decided, well, just out of curiosity, I wanted to compare the two equations from 10th edition to 11th edition. And you could see they're fairly close to each other. So we also have reliability factor. So there's typically that SC prime. I don't think the 0.5 is tied to the 50% reliability exactly, but they are related to each other. It's all based on 50% reliability. So the reliability factor adjusts to other reliabilities. It only adjusts the assumption. It does not imply overall reliability, right? So it just adjusts this, which has this line right down the middle that they've drawn through the scatter, right? So here's the 10th edition, and here's the 11th edition, and I don't think they're different anywhere, so I'm not sure why I put it in there, except maybe they just didn't give all these 99999s as part of that. It seems a little foolishness. So here's a repeat summary, and here's 13. You see that 13 right there? That says the reliability factor given here is to account for the scatter in the figure data only and is not part of a complete stochastic analysis. The presentation in this text is strictly a deterministic nature. For a more in-depth stochastic relation, see Budynas Nisbett citation. Okay. So anyway, we're trying to make it clear that we didn't make our answer more reliable. We are just trying to adjust for reliability effects as it applies to this guy right there. And then lastly, the miscellaneous effect can be used for other things. So it's a reminder to consider other possible like residual stresses, direct characteristics of cold working, case hardening, which is interesting right here, because when you case harden something, the surface becomes hard and stronger, but the inside remains nice and gooey and chewy and ductile, right? So we're making a more of a brittle type of outside thing. So that might be something we want to consider in this. Corrosion, definitely always a problem. Surfing, electroplating or metal spraying, cyclic frequency, frettage corrosion. So we actually leave it off in the 11th edition. But here's my big warning: KF is not the same thing as big KF, which is the fatigue stress concentration. Although, ironically, in some books, they use a something like it, except they divide by the stress concentration in that spot. We don't do that in Shigley, so don't worry your heads about that. So I'll continue on with the example here. So in this example, we want to estimate the life of a cold drawn 1030 51 millimeter diameter bar, which is a rotating and loaded in a completely reverse torsion right there. So here's the idea. We get the properties out of the book. We adjust and get that SE prime. We use a surface factor because it did say it was cold drawn. So those are the values we use for cold drawn right there. It is rotating, so that's fine. So we don't have to use. We just have to use the diameter. We use the 51 millimeter diameter, and you note that these numbers are near 1 but below 1. There are sometimes they could be something a little bit above 1. The loading factor, because it's in torsion, we use 0.59. The temperature didn't say anything about temperature. It didn't say anything about reliability, and we're never going to use the miscellaneous factor for anything. So you put all those up together, and we have 99.7 megapascals is our now fully corrected endurance strength, is the term that we use for the thing. And we want to estimate the life at 150 megapascals. So what we use is we go ahead and we use 68 KSI. We know that that's going to be a 0.9 fraction F. I find that value right there. Oh, by the way, I needed to convert. You don't actually have to convert, I think, in the 11th edition, but you had to in the 10th edition to convert to KSI. So we find that F times SUT, and then that's just a shortcut. We can go ahead and just calculate it once and put it into and find for the A the coefficient and find for the exponent. So we have those, and we put the 150 inside there, and boom, we found 140,000 cycles. And if it's a good idea to have some type of frame of reference. So let's just suppose it's at 1200 RPM. That's only 120 minutes. And so this is what that looks like on an SN diagram. Here is the 150, and there's where it lands down there. And ta-da, we have it done, 140,000 cycles. We're going to continue with notch sensitivity in the next video. Hopefully I can fit all this stuff in there. The end. 18 minutes.